we're getting to the point where we're going to be adding up the terms of a sequence, and so it's sort of like we're going to generate three numbers now for every sequence. For instance, if I had the sequence 1/2, 1/4, 1/18, 1/16, dot dot dot, this is a geometric sequence where the r value is 1/2, which means that the sequence is getting smaller. And if I kind of make an n t of n chart, when n is 1, t of n is 1/2, when n is 2, t of n is 1/4, when n is 3, t of n is 1/8, and so on. I'm actually going to create another column, and I'm going to call that S of n, capital S of n. And S of n is going to be defined as the sum of the first n terms. The sum of the first n terms. So in this respect, S of 1/2, or sorry, S of 1 is 1/2, but S of 2 is 1/2 plus 1/4. In other words, this, if I kind of shift this down a little bit, and I shift this down, my n's are 1, 2, 3, 4, and so on and so forth, then S of 2 means this sum, 1/2 plus 1/4, which is 3/4. And S of 3 is 1/2 plus 1/4 plus 1/8. And so that'd be 3/4 plus 1/8, which is 7/8. And S of 4, as you imagine, would be all of this plus 1/16, which for this would be, let's see, 4, 1/16, that'd be 15/16. And you can start to predict what the rest of them are going to be. Now, we're going to deal with what that approach is later, but I just want you to get in the head what this means. So let's try another sequence. Let's try an arithmetic sequence of 2, 5, 8, and 11. And this is going to be where the d here is 3. And as a series, I can write it like this. And I can ask you, what is S of 3? Well, S of 3 would be equal to 2 plus 5 plus 8, the first three terms, which is 15. I could even ask you, what is S of 7? Well, to get S of 7, we're going to have to know what the terms are. So to get S of 7, I'm going to rewrite it as 2 plus 5 plus 8 plus 11 plus 14 plus 17 and plus 20. And then we'll add all of those up. That's 15, 26, 40, 57, 77. So basically, that's kind of where we're going. For one more little tidbit here, and this is kind of important for me to you guys to know, this sum is getting bigger. And we say that that is diverging, because it's just going to grow without bound. This sum right here is converging. It's not diverging. Yes, the sum is getting bigger, but the sum is converging. And if you look at the pattern here, you can probably predict what number that is converging to. I'll let you think about it. 1/2, 3/4, 7/8, 15/16. Eventually the terms are going to be things like, well, here's a fun one. S of 11 is going to be 2047, 2048. To play the little game that I actually just won this weekend. But that is getting very, very close to the number 1, but it's never going to reach it. So that sum is converging. We'll learn a little bit more about that later. For now, let's kind of explore how we can write this series is a little bit better than before. I'm going to number these two. Let's number this number 1 and number 2. Put a little break here. So I don't always want to write, or we don't want to write. We don't want to write each series as numbers. We want to use formulas, just like we did before. So what I can do is I can actually write a series. Here's a third example. And I'm going to say this series represents the sum, and this symbol means the sum of all the 2n over n squareds, where n starts at 2 and ends at 7. Now, we're going to learn how to take this to an actual expanded list of terms here. But let's go with what this means here. this notation means the sum of. And what this here is, this is the index, this is the lower limit, and this is the upper limit. And this literally means plug in n values and create your terms. Plug in n values and create your terms. So I'm going to start with plugging in 2, and I'm going to go 2 times 2 over 2 squared. Plus, then I'm going to increase that to 3. 2 times 3 over 3 squared. And we're going to go all the way to 7. 2 times 4 over 4 squared. 2 times 5 over 5 squared. 2 times 6 over 6 squared. And 2 times 7 over 7 squared. This form right here is called expanded. This form right here is called sigma. It's a Greek letter, sigma. And we're going to prefer the sigma notation rather than the expanded notation because the sigma notation is less writing, and it's a summary. It kind of shows that. By the way, what we have right here in yellow highlight is basically the formula for the sequence. You can see from that formula that the numerator was an arithmetic sequence, and the denominator is neither kind of sequence. It's actually just the squares. One thing I want to kind of keep in mind is that if I look at how many terms are in the expanded sequence, I have 6 terms. Well, I could predict that because if I took the upper limit minus the lower limit, I'd get 5, but then I'm going to add 1 because I need to include those. Think about it this way. How many numbers are there between 2 and 7? Well, there are 6 numbers if you include 2 and 7. 2, 3, 4, 5, 6, 7. There are 6 of these digits. And so if I take the upper limit minus the lower limit, but then add 1, I get the number of terms. So, number 4. We're going to write in expanded. I don't actually want you to add, just write in expanded. So we're going to go to the sum from j equals 1 to 6 of all the 3j plus 1s. So here's the expanded. Just 3 times 1 plus 1 plus 3 times 2 plus 1 plus 3 times 3 plus 1 plus, just want to make sure I'm still recording, and I am, 3 times 4 plus 1 plus 3 times 5 plus 1 plus 3 times 6 plus 1. And if I look and check, there are actually 6 terms here. 1, 2, 3, 4, 5, 6. And that makes sense. My number of terms is equal to the upper limit minus the lower limit, and then plus 1. And that would be 6 terms. So that matches. And so I've got all my terms down. Now if I want to simplify this expanded sequence, I can just simplify each term. 4 plus 7 plus, and it's beautiful, once you realize it's an arithmetic sequence, you can just keep going. 4 plus 7 plus 10 plus 13 plus 16 and then plus 19. 6 terms. But I didn't actually ask you to add them, so we're done with that one. Number 5, we're going to write in sigma. This is a little bit harder because you haven't done this before. So we're going to go 1/3 plus 2/5 plus 4/7 plus 8/9. Now the first thing you're going to want to do is figure out what is the pattern. And a lot of times we've done these problems where the numerator is different than the denominator. Well, if I look at the numerator is a geometric sequence with an r value equal to 2. So I'm going to just create the formula for that. T of n is equal to t of 1 times r to the n minus 1, or 2 to the n minus 1. The denominator is an arithmetic sequence with a d of 2. And its t of n formula is t of n equals t of 1 plus n minus 1 times the common difference of 2. And that's going to simplify to 2n plus 1. And so if I sort of take this and make this its own fraction, I'm going to get numerator sequence over denominator sequence. Then I'm going to do a sum from n equals 1. How do I know that n equals 1? Well, I created this so that this here is my t of 1. And if you plug in 1, you're going to get 2 to the 0, which is 1, over 2 times 2 plus 1, which is 3. So that works. Next thing is, how do I deal with this dot, dot, dot? Well, that's kind of fascinating because the dot, dot, dot is going to plug into here as infinity. And that's very possible. We don't have an upper limit. We're going to keep going forever and ever. And so this is the sigma notation that means this sequence here. Number 6. We're going to write in sigma. So negative 7 over 1 plus 7 over 4 minus 7 over 7 plus 7 over 10 minus 7 over 13. Now, if I really wanted to be sneaky, I would actually write this sequence as negative 7 plus 7 fourths minus 1 plus 7 tenths minus 7 thirteenths. But I'm not going to do that to you, because if I write it the way I just wrote it up here, you see that there are 5 terms, and you can start to see what the pattern is. Well, let's separate it to numerator-denominator again. If I make my numerator sequence have an r value of negative 1, and a t of 1 value of negative 7, then that's going to alternate negative 7, 7, negative 7, 7, etc. And if I make my denominator an arithmetic sequence with a d of 3, then my formula for that one is t of n is equal to t of 1 plus n minus 1 times the common difference of 3, or 3n minus 2. And so the sigma we're going to set up is going to be numerator sequence. Well, let's get that going. T of 1 is 7, so sorry, I didn't even finish that one. T of n is equal to t of 1 times r to the n minus 1. Okay, so if I kind of write that down, negative 7 times negative 1 to the n minus 1 over 3n minus 2, then I've got it. How does that work? Well, it works because if I plug in 1, I'm going to get negative 7 over 1. If I plug in 2, I'm going to, and you can kind of track that down. So my starting n is 1 because I set this first term as t of 1. Where did that happen? This actually happened right here when you specifically said my t of 1 is going to be the first term. You don't have to do it like that, but it's easiest if you do. Then how many terms do we have? Well, if I count them, there are 5 terms. So I'm going to want to put 5 as my upper limit. That way, if I do the difference plus 1, I have 5 terms. And I can even check by plugging in 5. Negative 7 times negative 1 to the 5 minus 1 over 3 times 5 minus 2 is equal to, that would be negative 7 over 13. And that is actually my 5th term. So that's a check. That's kind of a good check to do. Check the last term sometimes. And so this is a perfectly acceptable answer for that. That's enough for right now. There are more examples in the book and other ones that you can see, but that should get you going.